Good morning, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located at Dundigal. Today, my topic of discussion is Bayesian method for inference. So, in the last class, we started what is Bayes law, what is Bayes rule, and how could we practically interpret Bayes rule, and how can we prove the Bayes rule, and what are the different names of Bayes rule, etc. Now today we are going to see the Bayesian approach in making inferences. Okay, so let us look into the details. So first and foremost, before going to the Bayesian methods for inference, we'd like to start first understanding the difference between frequentism and Bayesianism. See, generally we have two approaches in assessing or expecting something that is going to happen. Okay, first one is frequentism. It's an approach. Okay, generally we will apply this practically to estimate or assess something. And second approach is Bayesianism, which is little wiser than frequentism. Let us discuss what do you mean by frequentism and what do you mean by Bayesianism. As mentioned in the first post of the series, machine learning is mainly concerned with prediction. I told in the last class that in machine learning, most of the time you have to predict the data about the missing features of the data, and you have to estimate the features to the maximum possible extent in a better way. So that is the major task. While analyzing the data, there might be missing features, and the machine learning algorithm always takes care of how to predict the data correctly, how to predict the missing features correctly. So whenever the word prediction comes into our course of discussion, we must resort to the probability techniques. So in this concern, definitely we must be resorted to probability. So in this post, we are going to look at the two main interpretations of probability frequency. I mean, there are two approaches in using probability to predict something. The first approach is called frequentism, and the second approach is called Bayesianism. Okay, the frequentist or definition of probability, nothing but you can understand it as a classical definition of probability, is based on frequencies of event. That is, out of n times, suppose m times happen, then the probability of happening of A will be defined as m by n. This is called frequentist definition or classical definition of probability. Okay, whereas Bayesian definition of probability is based on our knowledge of events. When it comes to Bayesian approach or Bayesian definition of probability, just you don't base on the current happening, okay, or the previously happened. Apart from that, you will take the latest information and you will update your probability by adding the latest things or latest information, and you will revise the probability. Again, revised probability will be helpful to get updated with latest information. Again, that will be used to estimate the probability. So this is a cyclic process. That means we always use the updated information. So in the context of machine learning, we can interpret this difference as what the data says versus what we know from the data. That means what the data says and what we understood from the data. There seems to be very similar. You may say that what is the difference? Both are sounding same. No, it's not like that. Reading the lines is different from reading between the lines. When you read the lines, it may give one meaning, and if you apply your analytical skills and if your analoging skills, to past experience, then you will understand the original meaning of the lines. So that is what data says will be less, but what you know from the data will be more helpful. Okay. So in Bayesianism, generally we will try to analyze the data, whereas in frequentism, just we will take the data as it is and we will predict. Okay. Now, analogy. Let us try to understand with a beautiful example which helps you to understand the difference between frequentism and Bayesianism. Suppose you lost your phone. You have forgotten your phone and you are in a hurry to come to college, but you're searching, you're not able to find. In that instant, where did you lose the phone? That is the question. To understand what this means, I like to use this analogy. That means he's giving a beautiful analogy which helps you to understand the difference between frequentism and Bayesianism. Okay. So imagine you have lost your phone somewhere in your home. You use your friend's phone to call your phone. As it's calling, your phone starts ringing. It's not on vibrate. Okay, here, how will you search when you lose your phone? Generally, you'll take your homemate's phone or your roommate's phone or your friend's phone, your mother's phone or your sister's phone, and you will give a ring. And uh, assuming that here we assume that the phone is not in silence, not switched off, not in vibration mode. It is in activated mode. So when you try to call, it will ring, and by listening to that ring, you'll try to trace it. That's what generally we do, right? Now, how the frequentism differs from Bayesianism? Let us try to understand this example. How do you decide where to look for your phone in your home? Now the thing is, how do you decide where the phone is located in the room? How to trace it? The frequentist would use their ears to identify the most likely area from which the sound is coming. The frequentist will just follow the sound, and basing on the sound, he will, along with the sound, he will go and he will try to find the phone. Okay, that means his most likely area from which the sound is coming, from this area, this room or that room or from the back. Basing on the direction, he will follow the sound waves and he will try to face it. But however, the Bayesian would also use the ears in the Bayesian approach, not only using your listening skills or listening power. In addition, they would recall which areas of their home they have previously lost their phone and take it into account. That means you are thinking in two perspectives. One is you are trying to catch the sound, and even then sometimes you may be confused where the sound is coming. At the same time, you will also think that previously when you have forgotten your phone, in some instances where you have forgotten, might be in a bathroom while you are bathing, or might be in a dining room where you are taking your breakfast. So you'll try to recall those places, and you will also search those places if the phone is in vibration. So it's a two kinds. I mean, you are thinking in two perspectives, basing on past knowledge. Pastly, where did I forget? And last week also I did the same thing. I forgotten my phone in bathroom, or I might have forgotten my phone in dining hall or while watching TV. So you will use that knowledge and also this sound. So you have more probability or more chance to predict where the phone is lost. So that is what Bayesian is. In the frequency, just you use your listening power, you just follow the sound wave. But in Bayesian skills, just not only listening to the sounds, but also you'll also recall the things when you have forgotten and where did you find. Okay, both the frequentist, the Bayesian use their ears when inferring. So in the both ways, you first major dependencies on your listening of the sound. But Bayesian also incorporates the prior knowledge of lost of phone in the previous cases. So past knowledge also taken into account. That is the thing you have to understand. That is the way the both methods differ. Okay, now the concept first. So, in order to understand these things mathematically, first let us try to recall what is conditional probability. Conditional probability is nothing but P of A given that B is already happened. Okay, probability of happening of A given that B is already happened is defined as P of A intersection B over P of B. Okay, P of A intersection B over B. Okay, that means you're trying to find out the probability of A. This is event A. This is whole sample spaces. Okay, then P of A means N of A by N of S. That means this circle area by this rectangle area. You can understand. But P of A given B means we'll have another event B. According to this definition, the chance of happening of A given B is already happened means this common area, that is intersection, divided by this second circle area. So this ellipse area divided by this circle area. This is what conditional probability. Okay, both in general probability or in conditional probability, you are trying to assess what is the probability of happening of A. But this is unconditional means there is no condition. That is why this would be like circle area divided by rectangle area. But here, when you impose a condition B, the probability will be like this common part area, that is this ellipse area divided by circle area. So this is called conditional probability. When you suddenly impose a new condition, the chances of winning or happening of event A will definitely might be affected. Okay. So now let us try to understand Bayes rule. In Bayes rule, which we use for revising the probability value based on additional information that is later obtained. In Bayes rule, what do you do? He's telling what we do in Bayes rule in a general way, not in a mathematical way. First of all, he's telling that in Bayes rule, you will try to revise the probability, okay, basing on the additional information. That means you might have a sense of P of A, but you will revise that into P of A given D with the additional information D. That's what it is sensing. Okay, it is telling us, communicating us. And one key to understanding the essence of Bayes' theorem is to recognize that we are dealing with sequential events. Second important thing of application of Bayes' law is that you will apply Bayes' law when there is a sequence of events happening, E1, E2, so on here. So first and foremost, Bayes' law is applied to revise the probability when a latest or additional information is received. That is the first root cause of application of Bayes. Second reason for applying Bayes' law is when there are sequence of events happening which are mutually exclusive, then also you will try to apply Bayes' law. Okay, to assess which one is the reason, which one is the cause for an effect, cause and effect relation. Okay, whereby new additional information is obtained for a subsequent event, and that new information is used to revise the probability of the initial event. That means what you will do with this additional information, how do you revise the probability basing on this additional information? Simple. You will construct a condition probability that suppose EK is happened. What is the probability that the reason is, the cause is EK if A is happened? Okay, that means you are revising the probability of EK. Okay, you are revising the probability of EK with the help of information A is already happened. In other sense, you are checking how far ek is responsible behind happening of a. If a is happened, what is the probability that it is due to ek? So there are two ways of interpretation. Okay. In this context, the term of prior probability and posterior probability are commonly used. See, this is prior probability. This is posterior probability, because this is already you have with you based on your past experience or general. But this is posterior of receiving the latest information A. You have revised it. So this is posterior. Post means later. Prior means had before. Okay. Right. What is prior? A prior probability is an initial probability value originally obtained before any additional information is obtained. That means prior probability means simply P of ek. That is without any additional information, what is the probability of happening of it? That means you have this idea by your past experiences, and this is already fixed. You know this because you have been observing this since many times. Okay. A posterior probability is a probability value that has been revised using additional information that is later obtained. It's P of ek given A. Okay, probability of ek given A, posterior probability. That means when additional information A is given, what is the probability that ek given A? That means what is the effect, what is the change in the probability of ek, assuming that A is happy. This is called posterior probability. Okay. Now, Bayes' theorem formula is stated as like this: P of A given B is equal to P of A into P of B by A divided by P of A into P of B given A plus P of A complement dot P of B given A complement. Okay. So, here you are assuming that you know P of A, probability of A winning a game, winning a match, or probability of India will win the match, probability that India will win the match, that is P of A. Say it is 60%. Probability that India loses the match against England, that is say 40%. Okay. Now, you had a latest information that that is B. Probability that even though there is a rain, B means rain. B means happening of rain. Okay. India wins. That is say 10%. Probability that when there is rain, England won match against India, that is say 7%. Okay. Now you want to calculate, you want to revise the probability of the winning of chances of India, assuming that rain has happened in the next coming semi-final. That is assuming that rain has already occurred. What is the probability that India will win the match? That is called revision. Okay. This is a conditional probability. For that, generally according to the definition, we have to go like this: P of A intersection B given P of B. But what does it sense? This sense that probably that India and England both wins, but it never happens in a 2020 World Cup match. Only one team can win if match happens. Okay, unless it abandons due to rain. If match completely happens, only one team can win. So this definition won't work there. So how to find probability that India will win, even though or assuming that rain has definitely happened. Rain is definitely happening, going to happen. So what is the probability that India will? So for calculating this, Bayes is proposing an alternative formula because this formula is not working. He is proposing the formula that that it's a ratio that India wins given B by A by P of A into P of B by A plus P of A complement into P of B given A complement. This is the uh, alternative formula to find the revised probability P of A given B. So this is called Bayes law, which acts as an alternative to find a conditional probability or revision of probability or updated probability or the cause probability of cause. Okay, so that is why it has a great practical importance in so many areas, especially in machine learning. Okay, um, see the following example which illustrates us above expression, but also see the alternate method based on more intuitive application. So Bayes theorem, of course. Here we are seeing an application. We'll start with a simple example that I think nicely illustrates the difference between the frequency. Yes, now we understood what is Bayes law. Okay, now after understanding Bayes law, let us try to understand in a practical problem how frequentist and Bayesian approach will work. Here I am taking an experiment. A coin flips head up with a probability mu and tails with a probability of 1 minus. Of course, they are mutual exclusive and calculus exist. You know that if mu is the probability of happening of head, automatically probability of getting tail will be 1 minus nu. Failure is equal to 1 minus x. You flip the coin 11 times and it ends up with heads 8 times. Now, would you bet for or against the event that next two tosses turn up heads? Suppose you started a game to toss coin for here's given at 10 times. Let us assume not 11, 10 times or 11 times. And out of them, already you have done 8 times. Okay, now you have an 8 times, you flip the coin for 11 times. Out of 11, 8 are heads and 3 are tails. Okay, 3 are tails. Now you are going to flip the coin for 2 more times. What is the probability that these two will be again heads, given that already 8 heads happened? So it's a conditional probability. Assuming that already 8 heads happened, what is the probability that next 2 more times are also heads? That is the what conditional probability. Now, how here we are going to apply frequentist techniques of estimation or expectation and Bayesian methods of prediction. Okay, let's see. Okay, we have we have traded as a random variable. 1 means head and 0 means tails. That means we are mapping head comma tail to 1 comma 0. That is this function. Okay, then probability of getting 1 will be we are taking nu or theta here, and probability of getting 0, that is tail, is 1 minus theta automatically. Now our data is telling that out of 11 times 8 are heads, 3 are tails. Okay, now we want to estimate in the next 2 times what is the probability that the next 2 times is also heads in a row. Okay, now if the probability is less than 0.5, we will bet against seeing heads in a row. But if it's generally when we will bet in favor of that event, when the probability of that event is more than 50%, then we will surely we will be confident on betting on that event. If the probability is less than 50%, then we fold. We never feel that that event is favorable to us, and we will hesitate to bet on that. We will bet against to that. Okay, so more than 50% probability means it is favorable to the player. Less than 50% means it is not favorable to the player. That's what we understand. Okay. Now, in the frequentist approach, he'll use maximum likelihood estimation. He'll use maximum likelihood estimation, and by using maximum likelihood estimation, he'll try to find the value of nu. Okay, the parameter nu, and or theta. You can here sometimes we are using theta, sometimes new, so better we switch, we confirm it as theta. We want to maximize theta so that the probability will be more accurate. That is called maximum likelihood, which already we have discussed in the previous fourth module. Okay, so in frequentist approach, which technique you are going to use? You are going to use maximum likelihood estimation. Okay, but let us check what happens in this particular case by using maximum likelihood estimation. 11 trials, 8 success. Okay, then because binomial, because head and tail, 1 and 0, that means binomial, we are using binomial distribution. So it will be P of D given theta, or maximum likelihood will be, generally we denote it as L of theta is equal to NCR. 11 times we got 8 times head. The probability of getting head is theta, so theta power 8. The probability of not getting head is, or tail is, 1 minus theta, 1 minus theta power 3. This is our likelihood function, MLE. Okay, now we take L of theta here, 11 C8 theta power 8, 1 minus theta power 3. Now we will apply logarithm on both sides. Apply log on both sides. Then what happens? Log of L of theta is equal to log of 11C8 plus log of theta power 8 plus log of 1 minus theta whole power 3. Why it happened? Simple, log mn. Log mn means log m plus log n. That is why we have split it into addition. Log m plus log n plus log k, like that we have it. Now, when you see this log m power n means n log m, n log m. By using that, we get log 11C8 plus 8 log theta plus 3 into log 1 minus theta. This is what we got. Okay, we call this as small l of theta, which is called like log likelihood. Okay, so let us write log likelihood once again. What we have obtained? We obtained L of theta is equal to log 11C8 plus 8 log theta plus 11 minus 8 log of 1 minus theta. Now, differentiate L of theta with respect to theta. What happens? L dash theta is equal to 0 plus 8 by theta plus 3 into 1 by 1 minus theta into minus 1. Okay, differentiate L of theta with respect to theta. That means L dash theta is equal to constant derivative 0, log x derivative 1 by x, log x derivative 1 by x, chain rule, it becomes minus 1. So what we get, let us assume L dash theta is 0, then what it becomes? 8 by theta is equal to minus 3 by 1 minus theta. Okay, 8 minus 8 theta is equal to minus 3 theta. Okay, that means 5 theta is equal to 8. Theta is equal to 8 by 5. Theta is equal to, what do we get? 8 by 5. Okay. Sorry. 1 minute. It's is it it's what is the derivative? 1. 1's derivative is 0 minus 1 by 1 minus theta. Okay, it becomes oh yeah. I understood. It's minus 8 by theta, and hence this will be plus 5 theta. That means minus 8 theta goes to 8 minus 8 theta minus 3 theta. That means this becomes plus 3 theta, and hence it becomes 11 theta. Sorry, it becomes 11 theta is equal to 11 theta is equal to 8. So theta is equal to 8 by 11. Okay, so theta is equal to 8 by 11. That is what we have written, which is nothing but 73% approximately. So according to MLE expectation, probability of getting next tail as head, next trial as head is 73%. Okay, one time, 1 minute. So its probability of getting a head according to MLE is 0.73. Now we want it to happen for next two times. Next two times means you have to multiply it for two times. 0.73 into 0.73, that will be 0.53. So according to MLE, the probability of next two more trials here also heads, given that already 8 heads happened. What is the probability that next two also heads? Okay, this probability we estimated under MLE as 0.53. Okay, because this is more than 50%, because 53%, more than 50%, we feel that this bet is favorable to us, so we can bet on next two tiles will be head. We can bet because 53% means more than half, we can bet. Okay, now Bayesian approach we already discussed. In Bayesian approach, posterior probability will be there, and by using that we can write P of d by theta given d can be written as d given theta into P of theta by P of d. Okay, now this is our P of d by theta by using binomial distribution. P of d by theta is this. Okay, and P of theta will be by using gamma distribution. We can come to an estimation that P of theta could be gamma distribution, the famous probability distribution. By using gamma distribution, we'll come to or beta distribution and gamma distribution. We'll come to know that P of theta will be gamma alpha into gamma beta by gamma alpha plus beta, theta power alpha minus 1 into 1 minus theta power beta minus 1. Okay, so we have P of theta as well as we have P of d by theta, which we could substitute in the numerator. So P of theta by d, here alpha is 8, beta is 3. So what happens when we see this in the gamma function? See here, we are not touching this. Here, if we expand gamma function, gamma function definition is integral 0 to infinity e power minus x power n minus 1 dx. By using this, we can approximate this constant with, we are replacing that with this. Okay, we will reach this. We will reach that, and assuming alpha is equal to 2 and beta is equal to 2 in the beta distribution, and what happens? See here, gamma of alpha plus gamma of alpha into gamma of beta, okay, by gamma of alpha plus beta. That means gamma of alpha, that is getting 2 heads, so, or gamma of alpha means 2 heads, and already we got 8 heads. Okay, so it would be 8 minus 1 by 2 heads plus 8 heads plus total number of times tossed 11 times. Okay, minus how many times we have to toss, that is 2 times. We are getting 9 by 13, which is nothing but 69%, 0.69. Okay, and so what happened? 9 by 13 for one time, 9 by 13 for another time, that means it becomes 48%. So basing on Bayesian approach, what we are observing, only 48% of chance to get next 2 times head. Okay, so in the Bayesian approach we got only 48%, but in the In the frequentist approach we got 53%. So what we feel that frequentist approach has more, showing more chance of happening of the event. Okay, right. Now, so summary, frequentism is based on frequencies of events. Bayesianism is based on our previous knowledge of events. Okay, the prior represents your knowledge of the parameter before seeing the data. The likelihood is the probability of the data given values of the parameters. So frequentism means it based on only frequencies m by n. But here we have to take the previous knowledge of the happening of the event. Prior represents your knowledge of the parameters before seeing the data. Okay, and likelihood is the probability of the data given values of the parameters. So here in the likelihood, you will assume parameter to have some value and you will try to find the probability. In the prior, you will try to find the probability assuming parameter is known. Okay, there are the differences. Okay, now the posterior is the probability of the parameter given the data. Prior is when data is given, what is the parameter? Okay, probability of the parameters. Prior means when parameter is given, what is the probability of data? Where posterior means probability of theta given d. That means when data is given, what would be the parameter value? Okay, Bayes theorem leads to the prior, likelihood and posterior display. MLE just estimates the frequentist use. Okay, MAP means maximum a posterior estimate, which is Bayesian estimate. That means MLE means maximum likelihood estimate, which is frequentist, and MAP is the maximum posterior estimate, which is Bayesian use. Okay, so in prior we just write P of theta, but in parameter in posterior we write theta given d, because we have additional information of data, that is d. Okay, now we will see one problem to understand Bayesian approach and we will close our discussion. Before we know that the survey subject smoked a cigar, there is a 0.51 probability that the survey subject is male. That means we know that in a town 51% of the males, suppose it is an orange county. Generally we call in Britain, the states are known as counties. We call in our India, we call state of Andhra Pradesh, state of Telangana. In England, in USA we call them as provinces. Okay, in UK we call them as counties. They call Surrey the county, and Sussex county. So like that they have different names. So they have a county called Orange County. In that county they have an assessment that 51% of the adults used to have smoking habit. Okay, now the revised probability of a subject has smoked a cigar is 85%. Okay, that means probability that m given s means smoking, m means male, f means female. So probability that the probability of a smoker is found, probability that he is a male is 0.853. This is, but actually what we have, 51% of the males in that county are smokers. We have already this idea. In that Orange County, 51% of the males are smokers. But now latest what we have seen, when we found a guy who is smoking, the probability that he is a male, that is 0.853. This makes sense. The likelihood of male increases dramatically with the additional information that the subject smokes cigars. So instantly the probability may raise. Okay, generally we have this probability, but in that instance when we found a smoker who is smoking, suddenly the probability of likelihood of event will be raised. That's what he's telling. So, according to the data in the Orange County, 51% of the adults are males. Okay, and we can understand that males are 51% and females are 49%. Okay, and it is later learned that 9.5% of males smoke cigars. That is 9.5%. P of S given him, and 1.7% of the females smoke cigars. That is F by M is equal to 1.7%. Okay, so of course, females, why they resort to smoking, maybe due to some mental health issues, okay, or abuses. They may go into trauma and they may be addicted. Okay, that is a different thing. Now we have this information. P of M is 51% and P of female or M bar female is 49% in that county, Orange County, and probability of uh, C given M, that is cigar smokers in males, is 9.5%, and probability of C given females, that is cigar smokers in females, is 1.7%. Okay, that is what we have written. Okay, you can understand. Now, after having this, we are asked to calculate if we suddenly found a cigar smoker. Suppose probability that if a person found smoking a cigar, what is the probability that he is a male? Okay, then here it is given that he is smoking. That is why we can write C is already happened. Cigar smoking is already happened. Probability that he is a male. So condition is cigar smoking, and the probability we want to calculate is he is a male. So P of M by C. According to the Bayes law, P of M by C will be P of C by M into P of M divided by P of C by M into P of M plus P of C by M bar into P of M bar. Okay. Then P of C by M means 9.5%. 9.5% means 0.095 into how many males are there in that county? 51%. 0.51 by 0.095 into 0.51 plus probability that smokers in females is 1.7%, that is 0.017 into how many women are there in that county? 49%, 0.49. Okay, now if you calculate and simplify, you are getting this answer, that is 85% of the chance that if you found a smoker in the city, the person will be a male is 85%. Okay, that means it is raised suddenly by the instances. General probability has been raised to 85%. Okay, that's what we have calculated, and in this way we could understand the frequentism uses maximum likelihood estimation, and the Bayesian estimation uses MAP, that is maximum posterior approach. So both the ways we'll try to predict the missing features of the data. So with this, I'd like to conclude today's topic, that Bayesian methods of inference. And in the next topic, in the next class, we'll meet with one more important topic from the fifth module. Thanks for your patience listening. Thank you all.
Like, share and subscribe. hit the bell icon for more updates.